Welcome everyone to Tofu Tech Talk. This is a little show that I host where I invite Twitch streamers with STEM backgrounds. But today is a very, very special guest because this is not a Twitch streamer. We have actually a YouTube streamer, Z. Z, please introduce yourself as much or as little as you'd like.
Well, speeding at sea, it's me, Z. Hello, everybody. My name is Syzygy Altair, but you can just call me Z for short. I am a physics, astrophysics, maybe even a little bit of aerospace VTuber, and I stream primarily on YouTube. I am a VTuber at night, but during the day, I do galaxy astrophysics research. And thank you so much for having me. I'm so excited to be on the Tofu Tech Talk.
Excellent. I'm so glad. And you're actually our second VTuber, and this is how we actually met. Sidair shared, I think, something I posted on Twitter, and you found out that I teach physics and do physics stuff on Twitch and contacted me. So thank you so much for, reaching out. And yeah, if you guys ever have recommendations or no, make sure you don't hesitate to send me an email like Z did. Z, can I ask, what is your username? So maybe some people can recognize what the username is all about. But if some people don't, what does it mean?
This is a question that I get a lot, including how I pronounce my name. So the word syzygy is a really interesting word, not only because there are no vowels in it, but it's actually an astrophysical term. It refers to when three celestial bodies are in a straight line. So, for instance, that can include a planetary alignment when three planets are in a straight line. It can include an eclipse when, for instance, like the moon is in between the sun and the earth. And I just thought it would be a pretty cool name to have, and also a great educational opportunity. And it's also one of the best words that you can use for hangman because nobody can guess with all of those crazy letters and non-vowels in there.
So wait, you said it's three celestial bodies. So an eclipse, by definition, it is right? Because there's Earth, the Moon, and the Sun. That counts then, right?
Yep, that also
Okay.
counts.
Nice, love it. What is, if it's all right to ask, what is your field of research? What are the areas that you're interested and you love to talk and educate about?
Well, in general, a lot of my content tends to focus on astrophysics. Um, I'd say my area of expertise is certainly astrophysics. I love studying galaxies. I love studying the earliest galaxies in the universe and understanding how they have formed and evolved over time, which has been really exciting given the James Webb Space Telescope allowing us to peer back further into the universe than we ever have had before. So I tend to focus on a lot of astrophysics content, but I have to be honest, all of science excites me, and what excites me even more is getting other people excited about science as well.
I can definitely relate to that. How did you get started in this business of physics, science, and everything in between?
Oh, I actually had an amazing fifth grade science teacher. Oh, she was incredible. She had a bunch of animals in her classroom, like a snake and like a chameleon and all these things. And she was the one who told me to read some of Neil deGrasse Tyson's books for the first time. And I was just immediately hooked. I didn't really understand any of the science that was going on in the books, but I just really loved reading about it and learning about black holes and some of these really extreme objects in the universe. And I'm really thankful that I had a figure like that. I'm actually curious how you also got started in physics as well, because I feel like a lot of people have very different stories.
Yeah, unfortunately, mine isn't. I have had a few people on TTT, and people have amazing things to share about their story, about their background. Mine is very boring. It's a series of unfortunate events that just like landed on my lap, or things didn't work out, and I just kind of veered into it. So there was no moment in my life where I was like, oh yes, I definitely want to be a physicist. It just happened, you know, one path to the other. And well, we are here now, so it can't be all that bad. Um,
Woohoo!
Definitely. Explain your dress. Now, I know what this image is, but if anyone in the chat recognizes your dress. Oh, in fact, before you answer that question, just a big shout out. There's loads of people here. More than welcome. You're all very, very welcome. I just want to highlight if you guys have any questions for Z, Make sure to log them using the channel points. That way I can keep track of them, and I will ask Z in the second half, or the later portion of the stream, all the questions. So make sure you can log your questions in using the channel points. It's only 50 points, so if you follow me, you get like 6 questions already. So yeah, totally baiting you into following me. Now, sorry, apologies. Could you explain the image on your dress?
Yes. So my dress is the cosmic microwave background. And that's basically the first light of the universe itself. So when the universe was very, very tiny, just after it was born, there were a lot of high energy particles just stuck together, like all together. And after a certain point, the universe had expanded and cooled to a point where all of a sudden these photons were able to be released in the universe. Of the cosmic microwave background is what we see all around us when we look in the night sky. And it's very faint, obviously, considering that it has taken, it was released like 380,000 years after the Big Bang. And so it's obviously very faint. But by studying the cosmic microwave background, it shows us what the distribution of matter was in the early universe. So I guess it's might be a little hard to see, but the cosmic microwave background that I'm wearing has some red regions, some blue regions. Those represent overdensities and underdensities in the early universe. And so by studying the cosmic microwave background, we can look at how those overdensities have now become the galaxies and the galaxy clusters that we see in the universe today.
Sorry, I was muted. um, I didn't realize that that's how. For some reason, I know the image, the infamous cosmic background radiation image, but I never questioned what the red and the blue and everything else was. I just turned off my blue lab background just in case people wanted to see the distinction, because you're kind of blending into my blue background there, unfortunately. So the red dots form, they're the hotter regions, I'm going to assume. And they form the galaxy formations. And when I say hotter, I'm guessing it's only a couple of degrees, because the cosmic background is about 2 Kelvin. So it's only ever so slightly above zero. And so I'm guessing the red is ever so slightly more above. Is that fair to say?
I'd say it's probably better to represent it as like over densities and under densities in the universe,
Oh, I get it
because
now. Okay,
I
of matter
believe that
specifically.
yeah, the temperature difference is very minor if I recall correctly.
Mm.
Um, so yeah, it's more like a matter density distribution.
That's fair. And you mentioned it earlier that you love to study and discuss the formation of some of the earliest galaxies. Question: what is the earliest galaxy? Do you know? Do we know?
That's a great question. And we have taken photos of galaxies that have emerged basically just after the universe was born. Like, I think maybe even like a few million years after the Big Bang. Um, and the reason why this is such a great question is because we have photographed these galaxies, but we know very little about them. For instance, many of these galaxies are just a few pixels in our James Webb images. And we've been noticing that these galaxies look a lot more massive than we anticipated, which is surprising because if you imagine a galaxy coming together, it should take time to form and assemble. And we're noticing that these galaxies are humongous, these baby galaxies, which means that maybe there's something wrong with the way that we're interpreting our observations, or maybe we need to rethink our galaxy formation theories.
Oh, that's really interesting. I'm trying to remember any stuff I remember from galaxy formation, but I swear I can't remember a single thing from any of my classes. I don't know why. But oh, I know one thing. That's no, it's not a galaxy thing, but I suppose it is a galaxy thing as to why things spin. It's got to do with the momentum of things spiraling inwards to form themselves. Is that right? Am I right in saying that?
Yes, so there's a lot of like angular understanding of angular momenta, and angular momentum conservation, in how galaxies spin. So that's correct, yeah.
Okay, nice, nice. We have just a quick question. I usually jump at the questions at the end, but if it's on topic, Goober's asking, is the CMB the lowest natural temperature?
Ooh, well, I guess the universe, when the CMB was originally emitted, it was much hotter. I guess the
Mm,
CMB does have a uniform temperature of around 2.7 Kelvin.
yeah.
And everywhere we look around us is going to be the cosmic microwave background. That being said, there are places that are colder than the cosmic microwave background. Um,
Oh.
for instance, there is this one nebula called the Boomerang Nebula, and I don't know if you can pull up a photo, but
I can look it
for
up
those
and
of you
share
in,
it.
yeah, it has a very funny appearance. If you play the game Among Us, it like looks like an Among Us.
Let me see. I have the Boomerang Nebula here. I've popped it up and I will do a quick display, a cheeky display capture for everyone to see it. Where's my display capture? There we go.
It looks very sus.
No, yes, that's the right one. And then I pull up this. Ta-da! Is this is sorry? Are you aware of what I'm streaming?
Wait, I see it on your stream, but I think you
That's the
should
wrong
just
one.
look at there's a National Radio Astronomy photo here. I can also send it the link to you.
Oh, is it the? Oh my god!
Yeah,
Oh my god! I see it now. Oh my days! Holy
I actually
smokes!
did I actually didn't know that this nebula was a thing until the Orbeez, which is like my YouTube community, on stream was like, "Have you heard about the Boomerang Nebula?" And I was like, "No, I haven't." And I searched it up, and it's so.
Oh, that is amazing. It really does look like the Among Us characters. Very, very. Oh wow. Oh, so that's a very, very cold nebula. Do you know why, or do we as humans know why it's so cold?
Yes, so the Boomerang Nebula, I think I just had to quickly search it up. It is
Mm,
about 1 degree Kelvin. And I guess you might know a bit more about this considering that you do like physics education. But the way that this works is that the Boomerang Nebula is a nebula that is surrounding a dying star.
mm-hmm.
And this dying star is sort of shredding out its outer layers. Oh, sorry. It looks like my microphone just disconnected. Let me just
Oh no, it's okay.
replug that.
We're still hearing you.
Oh, okay, great. Yeah.
Maybe
All right,
we're
can you
not
hear me?
using the right mic the whole time.
Yeah, I was on my other not so great mic.
Oh no, we hear you fine. Yeah.
Okay, great. So the Boomerang Nebula has a dying star at its center, and the star is basically ejecting its gas at a really fast rate.
Mm-hmm.
And the expansion of this nebulae causes adiabatic cooling. And so it actually cools the nebula to temperatures colder than the background radiation, the cosmic microwave background radiation of the universe.
Okay. I
Hmm.
haven't taught my students, by my students I mean my chat, about adiabatic stuff yet. I would love to teach about the Carnot cycle and everything like that. So eventually my lab rats will learn about those things. I'm trying to call them my students because accidentally during a real life lecture I called my students chat, and that is how so many of them found me as a Twitch streamer. So I have to be careful of that for sure. In one of the descriptions that you sent me about like what you do and what you educate, you mentioned general relativity. First of all, is there my question here is, could you explain to my community what is general relativity? And if you have any fun gimmicks or stories or history around it, please do share.
Well, my channel specifically has a YouTube series on special relativity. So general relativity is a little bit
Oh,
more
sorry,
advanced.
special. Yeah, apologies. Yeah, special,
Yeah,
not general. I got them confused again.
yeah. So special relativity is basically a way of understanding how things behave when we're approaching the extremes of the universe, light speed. Um, and so general relativity is sort of understanding like how does space-time curve and that kind of stuff. The point of what I did with the special relativity YouTube series was to basically understand some of the core foundational ideas That includes time dilation, which is the idea that moving clocks appear to tick slower. Length contraction, which is the idea that a moving object looks to be shorter than it actually is. And also concepts like causality, which is when one event happens after another. And all of these things are tied to special relativity and understanding a lot of Einstein's big ideas of how the laws of physics behave um, at these very high velocity frames.
Mm. We have a question of any explanation on the twin paradox. So, if you're aware of the twin paradox, could you explain it and maybe explain why it's a paradox?
Yeah, so I actually had a video sort of covering this. I had a more graphical approach in that video explaining sort of the lines of sight and that kind of stuff in that video. So that's on my YouTube channel. But the for those of you who don't know, the gist of the twin paradox is it's one of those like special relativity brain teasers that you need to sort of think about. The idea is that let's say that there is one twin, Alice, who stays on Earth, and then another twin, Bob, who travels at a spaceship at a speed like very close to the speed of light,
Hmm.
goes to another planet, turns around, and comes back to Earth. And the question is, sort of, there can be different questions like, after Bob returns from his spaceship, like what is the age difference between Alice and Bob because they're not the same? Also other things like what does Alice see when Bob goes to the planet? And there's some really funky behavior. The main conclusion of the twin paradox is that after the twin that goes to the planet comes back, Bob, in our case, will be a younger age than Alice, who was there on Earth,
Hmm.
because of time dilation. Um, which means that because the spaceship was traveling at a very fast speed, close to the speed of light, um, Alice and Bob experience the time duration to be different. And so it's sort of a cool little thought experiment and paradox to experiment with special relativity.
And why is it defined as a paradox? So, my question is like, so what if Bob comes back younger than Alice? Where's the paradox in the paradox statement, if that makes sense?
Yep, so I think the term for the paradox started because when you're first posed with the twin paradox with no understanding of special relativity, you would assume that
Ah.
the time that it takes both the twins, one on Earth and one in the spaceship, and if they come back, they should be the same age. But now that we understand special relativity, we know that one of the twins will age longer than the other.
Yeah, no, that makes sense. We love to talk about paradoxes here. If you're ever interested, I recommend you rereading or looking at Maxwell's paradox. And the reason I say I recommend it is don't do it because it pisses me off. Because it's not
Maxwell's
a
paradox.
yeah, Maxwell's one is a thermodynamic one and it angers me. It's about energy conservation and information being energy. Anyways, that's a
Oh,
different talk for another time, but in my channel we anytime anything goes wrong we blame Maxwell's demon. It's called
I
sorry
see, I see.
it's called Maxwell's demon, the paradox, yes. So thank you so much for explaining and teaching to our community many things. People were writing in chat, oh, the interstellar thing, and oh, this makes me want to read the three body problem. Now, I love interstellar. I love science fiction generally. I like the idea of science, and I love the idea of fiction. I know a lot of people, scientists, can be like, oh, this isn't accurate, this isn't okay. But my kind of gist is, as long as it's generally good, I don't really care about the fiction part. It's just a bit of fun. But have you read or seen the three body problem?
I did read the three body problem, but it's
Oh.
been so many years now that I actually want to reread it again. I'm actually curious if you have as well, because I feel like
No.
it's like foundational reading in physics for some reason.
I watched the TV show only because everyone kept telling me to do it as a physicist, and I grumpily sat down and watched it, and I criticized it to no end. I think the
Really?
problem I had with it is that it was very much still science fiction, but people were so the narrative that people were pushing to me is that this is very good science. The science in it is so amazing. You would love it. And personally, I think because I was told that, I sat there with a skeptic eye and judged it too harshly. That's kind of, a bit of self-reflection that I was a bit too mean to it. This happens to me before. Someone told me that Game of Thrones is as good as Lord of the Rings, or is similar to Lord of the Rings, and I watched Game of Thrones and it was a disaster. I hated it. So, it's just, you just can't compare those two things too much, I think.
That's a crazy statement because I mean, they're both fantasy, but I mean, Game of Thrones is like it's very different. Oh God. Well, that's a very interesting recommendation.
Yeah, someone said it, and because I love Lord of the Rings is on a pedestal for me. I came in with the judgmental, snarky kind of look on it. So again, nothing, maybe the books and the TV shows are great. I'm just being judgmental, and you know what? I can self-reflect and be aware that I am what I am. I suppose, like, I actually keep this question at the end, but because we were talking about the three-body problem and Interstellar, is there like a physics-esque or a sci-fi TV show or movie that you highly recommend that you think is really, really good and you enjoyed?
Ooh, oh, that's a tough one.
Do you want me to like
I
let you ponder on it for a while and we'll come back to it?
Well, I have a few answers off the top of my head.
Perfect.
So I do really love reading. So I have some book recommendations. Actually, somebody in chat just said Project Hail Mary. That was actually the one that I was thinking about right now. Um, any of Andy, I think it's Andy Weir. I don't know if I'm saying his last name right,
Yeah,
but
no,
Andy
that's
Weir's
right.
books, The Martian, Artemis, Project Hail Mary, were absolutely spectacular. There's a movie coming out for Project Hail Mary in
Ooh.
2026, which I'm very excited about. Um, I think in terms of TV shows, I really enjoyed the Apple TV show for Foundation, which was based off of a book by Isaac Asimov.
Mm,
But I only enjoyed the first season. I think the second season and the third season were not as interesting to me, but I really recommend the book for that. The world
yeah.
building was great. Dune is in my top series of all time. I've read the first three books. I actually think that they're working on another movie right now for Dune, which I'm very excited about because I think that for any of you guys who have read Dune, the first book is great, but I think the second book is what really brings the series to a nice close, better than the
Mm.
conclusion of the first book. I don't know, Tofu, have you read Dune as well?
Just only the first book. So I read first book
Hmm.
a few years ago, and I've seen only part one of the movie. I haven't seen part two.
Oh, you need to see part two. I mean, it's incredible. The Dennis, who's the director, did such an amazing job. It
Hmm.
was amazing.
We'll put Dune on the recommendation. And it's funny you mentioned Asimov's Foundation because I don't know about the other season, but I know season one was filmed in Ireland here, and I can show off that the person who got me into physics, or well, got me to do my PhD in physics, was my thermodynamics lecturer, and he was the advisor for Foundation. So I get to
No
I
way!
get to wave that
That's
flag.
crazy!
Now, people in chat will jump in, but the physics was terrible. I haven't seen it, so I can't judge. I've only read the first book of Foundation because I rather get through my robotics series instead. Asimov's robotics series.
Oh, I have not read that. What do you think of it?
It's really good. What I recommend is even if you're not into sci-fi or you're not into the series or you don't finish it, I recommend iRobot because iRobot is a collection of short stories because originally Asimov wrote a bunch of like little short stories in to publish in a sci-fi journal, but they're all around the premise of the three laws of robotics. But each story stands on its own, and it's really witty. It's really well written. That being said, it's been a good few years since I last read it. But when I read it, I thought, oh, this is so like crafty and so smart how the wording of the three laws makes it so interesting how robots can bypass it. So if you remember, I don't know if many people are aware of iRobot laws. They can't kill a human or they can't cause harm to a human. They can't cause harm to themselves. And what's the other one? No harm to a human, no harm to themselves, something else. Oh, Jesus. Can't think of it. But there's like a reason why certain rules are ordered in a certain way. For example, the one where they can't harm themselves has to come second after not harming others. As in, it's
Mm,
okay for a robot to sacrifice themselves in order to save a human life. That's kind of the biggest reason to the order of the laws.
I see. I see. Yeah,
Anyways.
I've watched iRobot, but I've actually never read the book or the
Mm.
books or short stories, but I will definitely give that a read. I actually just opened a new tab to remind myself to add that
Yeah.
to my Goodreads.
Ovaline, thank you so much for writing it. So the first law is don't harm a human being. The second law is follow the rules of a human being, and the third law is to protect its existence. But on in that order, and yeah, it's very good how the robots and the AI, and by AI I mean actual AI, kind of surpasses it. Anyways, that's a little bit of a side rant. But as we're talking about robots, one of the things that you post as well on your media and your descriptor is that you do a lot of electronics. Is it that you teach or you build stuff, or what's your kind of passion behind electronics?
Yeah, so I have done live soldering demos on my stream before. This was
Mm.
actually, I think, like several months ago. I was doing a wildfire relief campaign actually for the LA wildfires, and I thought it would be really great to sort of showcase that you can stream soldering. So I actually soldered a little hourglass on stream. Um, and yeah, I'd say electronics is certainly not my area of expertise, but I have sort of taught it and like presented on some like smaller projects on it before. And so I wanted to sort of share some of the stuff that I already had some like talking material on. So that was
Mm.
really a lot of fun. And I think it really comes to show that you can have these like live demos on stream and have people learn and get hands-on even through a screen.
Yeah, no, I watch a lot of YouTube tutorials to how to solder, little bits and bobs. So, I always say it like YouTube is a fantastic uh platform because I don't know how my parents survived, but I learned everything I know in this world about through YouTube. There's a few questions. I'll try and catch them as we're going through the chat, by the way. But number two, if you guys want to make sure I catch them, make sure you use your channel points so that it's logged and I'll never lose them. But I've caught Oval's question, related question. Are you concerned about the development of AI? I don't know if you're comfortable about asking, answering this question. You don't need to. But do you have any commentary on AI? And by AI, I'm assuming we're talking about Gen AI.
Yes, so I can say a little bit.
Mm-hmm.
I think that AI is basically becoming ingrained. I mean, it already is becoming ingrained everywhere. I do have to say that like AI has significantly improved just like workflow in general. There are so there's sort of two ways I can approach this. I think sort of from a like a research standpoint and from an education standpoint. So from a research standpoint, coding has become much easier, which means that researchers can sort of focus more on doing science rather than figuring out how to make a plot larger in Python, for instance.
Okay.
Um, but on the other hand, there have been a lot of concerns about AI in education. The reason for that is because when you have generative AI and you have a homework problem, you can ask the AI for the answer with skipping all of the steps that it takes to learn about the process itself. So let's
Mm-hmm.
say I have a physics question on kinematics. I can say, oh, what is the velocity as the ball reaches the ground? And the AI can say a bunch of stuff, but you can stop it and be like, no, just give me the answer. And it will give you the answer. Which means that, unfortunately, there has been a problem where students are sort of skipping the intermediate steps where they actually interact with the concepts and learn about the physics processes themselves. So that has definitely been a big concern.
Mm.
I've heard some solutions in which some people are considering doing like quizzes in between lectures, or trying to focus more on writing based prompts than or project based assignments rather than just homework sets. But I think it's a big problem. It's a big problem. And it's really a volatile space in understanding where is physics education going to go. I'm actually
Mm.
curious if you have any thoughts on this, considering you're doing physics education yourself.
Yeah, no, I mention it a lot. I do think that there's amazing strength in AI, especially in research science, kind of like what you mentioned. But also even, the what is it called? The Nobel Prize that was awarded for being able to predict and find molecules. That's kind of AI is so important, and I think that's where we want to premise. And I think the problem is Gen AI, and exactly what you said, where the study showed that the people who focus with using something like ChatGPT don't develop fully the thought process of solving a problem. And I kind of dislike this argument that a lot of people use where it's like, well, we have Gen AI now, the cat's out of the bag. It's the same thing as calculators, right? Long time ago, we didn't have calculators. Now we have calculators and we can calculate anything. And yet, look, the whole world didn't collapse. But I always point out that, well, hold your horses. When we were in school, I still learned how to do long multiplication. I still learned how to do long division. I still had to learn to solve problems before I was allowed to use a calculator. And it was so easy for the teachers to monitor. They'll just take away your calculator, or we didn't have calculators for a long time until you hit high school level, let's say. But you're absolutely right about ChatGPT, about putting an incentive. It's not a sort of incentive, but last, let's say, decade, because I have a bachelor's degree in secondary school teaching, I know what's going on in secondary schools, i.e. high school level as well. And for the last decade, there was a huge government initiative to initiate more project-based research or project-based learning. The idea behind it is that it's not all based on this last final exam that's worth 100% of your grade. Instead, you can do an experiment or a project at home that could be about 20 to 40%, so there's less pressure. The problem now is literally, as it's been implemented this year in Ireland, AI is at its peak. And so what's happened now is that we can't truly examine students as much as we should be able to. And instead, there's this whole Gen AI issue with a lot of the projects that are being done at home. And that's a huge problem at the moment. Look, there's pros and cons, and I think we generally agree with the pros and cons, and it is really worrisome. We as a group, many people of us will be one of the rare generations that can kind of problem solve, and if when the AI robots take over, people will look to us for answers.
Yeah, I think that's a great point though, because I feel like there have been ideas that, oh, now that you can do things like vibe coding, which is basically a term of just giving giving AI like a prompt and just giving them the description of the code that you need, and it just generates the code and you don't really go over it. Um,
Mm,
Now that there's stuff like that, there have been some people saying, "Oh, you don't even need to go to college anymore." But I don't think that is a right argument, because you still need to understand coding. And if you're doing physics simulations, for instance, you still need to understand physics so that you can
mm,
read over the code and make sure that the AI isn't hallucinating anything. And it's really
mm.
concerning because I didn't know actually that you were doing secondary education for your bachelor's, but it makes me think because even after COVID, the educational levels from like standardized tests have still not bounced back.
That's
And
right.
the question
Yes.
is, why? And I
Mm,
have a feeling that maybe a part of it is potentially due to AI and schools having to find new ways to keep students engaged, to keep students still questioning science, and to, well, I guess, using critical thinking.
yeah, no, you hit a really big nail on the hammer, because when COVID hit, everything had to go online. Everything had to do there was this self-assessment push, and then also straight after that was the AI introduction. And so we have this big gap of a generation of students coming in now. Chances are I'm going to get those students coming in soon, the first year in college, where it's going to be very prominent and obvious that they missed out on a lot of problem solving that we were able to do, or we were assigned to do anyway. Yeah, it's a bit worrisome, but yeah, I don't know how much more we can say about that.
Yeah. I'm wondering, have you thought of ways to sort of engage students? I'm also trying to think of different ideas. So I'm curious to hear what your take is on how you engage students in this like new era of AI.
Oh, so even though there's a difference between secondary school teaching and lecturing, right? When you're a teacher, you teach, and when you lecture, you lecture. I know that sounds a bit redundant of a statement, but they're actually two different things. So what I do is I don't lecture, I teach. Even to a big class of 100 students, I do teaching. I make them solve problems in between classes every like 10, 20 minutes or so. I go around the class, I check like a teacher the handful of students that I can reach. I also do a lot of demonstrations, which is very weird for a lecturer to do, but I'm very much inspired by a lot of the most eccentric physics lecturers out there. I think demonstrating is really, really important. And I always finish my class like 10 minutes early. It's a little thing that I do so that I give room for curious students to come down and ask questions. Or if there's usually a demo, there's additional demos at the end. Something like I'll bring the Van de Graaff generator and I demonstrate an electrostatic charge. And I say at the end of class, if anyone wants to stay behind, you can all get a nice electric shock if you're interested in it. And it doesn't seem that much, but let's say out of a class of 100 general science students, about 10 of them would come down, and actually a lot more. They'd come down and they have such good crack and such good fun, and it just inspires that curiosity as to why that happened, and they'll ask you why, and you'll get a feeling as to their thought process and how it works and where their mindset is. That's my only kind of advice or method of keeping my students engaged.
I think it's great that you're like walking around and interacting with students, because I think with lectures, it's very easy for students to sort of zone out, or nowadays with lectures being recorded, I've been hearing that, not many students even go to lecture, because why would they if they can watch it on a video and watch it on 2 times speed and get it through twice as fast? But I think I really enjoyed what you said about it being interactive, because I think when you're getting hands on, or if you're actually deriving something yourself, that's when you're using those like critical thinking skills. Um,
Yeah.
so you brought up amazing points there.
To everyone taking notes on how tofu teaches, but also the little things I do is practice stuff on Twitch, see how it goes. If my lab rats can pay attention to me, surely then my students can. But to each to each their own. I think I actually managed to fly through all my little questions. If anyone in my community has any questions that they'd like to ask. So we covered a lot of topics. We covered electronics, teaching, AI, special relativity, galaxy formation, which is your area. And we only really talked a little bit about the nebula, which was really, really cool. I suppose if anyone has any questions, please go ahead and log them in. But I'd just like to jump in. Is there any kind of like story or maybe really interesting anecdote you have about galaxy formation that you could teach us maybe for a couple of minutes?
Ooh,
This
I
puts you
mean,
on the spot, I know.
there are a lot of really interesting stories. I mean, I think right now is a very exciting time to be understanding the earliest galaxies in the universe. Not only do we have a lot of new, fresh photos from the James Webb Space Telescope, which is absolutely incredible, but we've also gotten to the point where we have a lot of really powerful computational simulations. We can simulate the earliest galaxies in the universe, and that is actually the direct way that researchers are sort of testing theories. Because let's say that you have a universe in a box, and you want to test whether a specific type of like physical process is at this certain scale. Then you can actually simulate and see, do those galaxies in that box end up looking like the galaxies we actually see in the universe? And our computational power has gotten so great that we're able to do that. So that is one really exciting thing. So not only are our observations really great, but our simulations are really powerful as well.
And have we been able to predict models? And this is wrong. I suppose because humans live such short lives, I don't think any of our models have come to fruition, or what's the word? We haven't been able to observe the models play out, right? As our lifespan is just a little bit too short on a cosmic scale.
Yeah, so in the nearby universe, or the universe around us, like let's say the Milky Way,
Mm,
the timescales are definitely much harder to deal with. But fortunately, the James Webb Space Telescope is sort of like a time machine. And the way that it works is the further back you look in distance also corresponds to further back in time. And that's
mm,
because the speed of light is finite. It takes time for that light that was emitted by the first galaxies to reach us. And so when we are looking really, 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 really far away, we're looking at the earliest galaxies in the universe. And so we sort of have a time lapse of how galaxies have evolved from the early universe to now.
mm. That's really,
So
really
that's
cool.
sort of, yeah, so that's sort of how we test our theories throughout time.
We have a question. Why are there different shapes of galaxies, and are they due to different conditions for the different shapes? That's a really interesting one.
Yeah, so there are three primary types of galaxies. There are spiral galaxies, like the Milky Way. There are elliptical galaxies, which, as the name suggests, are just kind of like spherical. And
Mm,
there are irregular galaxies, which are very funky looking. The reason why different shapes form can be attributed to many different things, but I'd say just in general, um, spiral galaxies form when the conservation of angular momentum actually like flattens it out into a disk, and
mm,
elliptical galaxies form from the merging or the coming together of many different galaxies. That's because merging galaxies tends to sort of randomize the star orbits, and so it destroys the disks themselves, and so it becomes more elliptical. And
mm.
irregular galaxies might also are also due to interacting galaxies. Um, so it's a lot of environmental influence, sort of how the galaxies have merged in the past, and also just like conservation of angular momentum and sort of these core physics concepts.
Mm. And in the center of our own galaxy, we have a black hole. Is that the current premise at the moment?
Yep, we there are actually supermassive black holes at the center of most massive galaxies, if not all. And yeah, so that's Sagittarius A star, a very cool name. And that's at the center of our Milky Way. And actually, one cool thing to share is that there's actually a photo of Sagittarius A star, which was taken with the Event Horizon Telescope. It's like this orange black blob. I think actually I just Googled it. It's the first Wikipedia image. Um, and that was an incredible collaboration. It's the Event Horizon Telescope, which is actually sort of like an Earth-sized telescope. Um, I don't know
Damn.
if, yeah. Um, and so the way that that worked is obviously building a telescope the size of the Earth would be incredibly challenging and incredibly unfeasible. And so what they did was it's actually a collaboration of multiple telescope observatories placed throughout the Earth. And when you combine the images taken from all of these observatories together, it's almost like you have an Earth-sized telescope. And that collaboration was how this image came to be.
Pretty, pretty cool. Is there
Yeah.
anything between galaxies, Chocolate asks? I'm going to assume
Oh,
the answer is space, no?
well, yes. So there's a lot of empty space. But one of the interesting things is that there is a lot of intergalactic medium, which is basically a fancy way of saying gas in between galaxies. And this is mostly made up of hydrogen. Um, but when you are in a galaxy cluster, so a cluster of galaxies, this gas can be incredibly hot. It could be like I think millions of degrees hot. It's heated by gravity, it's heated by shock waves from other galaxies, and it actually emits X-rays. And so some astrophysicists use this intra-cluster medium, this really high temperature gas, to map galaxy clusters and understand them. Actually,
Mm.
another cool tidbit, I don't know if you could pull up a photo of the bullet cluster,
The
but
what
some of
cluster?
the
Cluster? Sorry?
The bullet cluster.
Bullet cluster.
Yeah. I could probably also send if you just yeah, maybe here something that looks like this. The majority of the mass between these like galaxies in a galaxy cluster can also be dark matter.
Mm-hmm.
So what's being shown here, yeah, so there seems to be sort of like, oh yeah, I just saw it on stream, perfect.
Oh, sorry.
This is this is like an X-ray photo of the bullet cluster. And you can sort of see that it looks like a bullet like traveling through space. And
Mm-hmm.
what's actually going on here is that it's two galaxy clusters that have collided with each other. And one has actually passed through the other. And you can sort of see it with the sort of white regions in this
Mm-hmm.
image. But what's really fascinating about this object is that this is actually the first indirect observation of dark matter, if I recall correctly.
Oh.
And that's because the matter has traveled through each other and has interacted and really heated up. But what scientists saw in this image was that the dark matter actually just passed right through each other. And so there's a separation
Whoa.
between the normal matter that we can see and observe and the dark matter distribution. And so to sort of go back to the original question, like what's in between this empty space, in something like this with the galaxy clusters, there's a heck ton of dark matter. Um, so yeah, I just wanted to share that little cool tangent, if
I
that's all
actually
right.
had a question written down as well. What is your stance and opinion on dark matter? Because for a long time, when I first started my dig at science communication on Twitch, I was thinking about reading publications, right? You know, like that thing. And every freaking day there was a new publication on dark matter, and it was back and forth that it never existed. It's actually this, it's actually that, and all these little things in between. So I'm interested to know, first, I don't know if your research revolves around it, but even, you know, as a person who studies astrophysics, perhaps you can enlighten us with your own commentary on it.
Yep. So I guess I do know a bit more on the astrophysical side of things, but I think what you mentioned about, dark matter publications coming out so often
Mm.
can feel overwhelming for sure. And the reason for that actually is because the dark matter problem is a problem that spans all scales of the universe. You can approach it from the particle scale all the way to the galaxy cluster scale. And so it's really the most interdisciplinary, the most multi-physical, multi-scalar problem that you can encounter. Um, which is also very exciting because that means that there's multiple ways to test it. So I can sort
Mm.
of answer from the astrophysical side. In terms of astrophysics, because there is so much dark matter in galaxies, galaxy clusters, we actually have a pretty good constraint on how dark matter behaves at these large scales. The real question, though, is what is dark matter? And
Mm.
there's a lot of particle experiments that are delving into different ideas like I don't really know too much about this, but like axions and um, WIMPs, which are these like weakly interacting massive particles, both of which
I
are
love that
candidates.
name, by the way.
Yeah,
Wimps
WIMPs,
is
right?
so good.
Yeah, no, it's a great name. Whoever thought of it is great. Scientists are great with acronyms.
Definitely.
Um, but yeah, so at the astrophysical scale, we've constrained it pretty well. Now, the particle scale, there are various experiments that are being done to try to constrain what particles it could be, and lots of theorists and stuff like that. So it really is a complex problem. But we've simulated dark matter in galaxy simulations. Actually, we've gotten that down since I think like the 1980s, 1990s.
Mm.
Um, and so really the next step for understanding dark matter is like what is it made out of? And that's a problem that we've been dealing for a very, very, very long time.
Yeah, I hear that the next upgrade of the particle accelerator collider that they want to build is in hopes of doing research in dark matter, but I don't know. Personally, I think it's a bit ambitious.
I was wondering what is sort of your take on dark matter? I'm not sure if
Oh,
you've yeah.
yeah, my I'm kind of like a well observed bystander, I think, if that makes sense. That, you know, this is not my field of expertise, but I have enough classical physics to definitely understand that there is something there. But that's the idea. I think that's what everyone kind of agrees, regardless of what you kind of research or what kind of like postulate or hypothesis you push or narrative. I think we can all generally agree that there is something freaking screwing our data, and that's the reason why we call it dark matter. We don't really seem to see it, and there's this dark energy because we can't seem to really know too much about it. So it is what it is, and we kind of just accept it. And yeah, that's kind of my opinion. I can't have a very well informed opinion since it's not my research at all.
Yeah, I think it's just crazy though that everything we can see and touch around us is just 4% of the universe. You mentioned dark energy, which is great because I mean, that's an even larger portion of the universe and we know even less about that. So,
Yeah. Tarek asks, how do we know that the galaxy we see the furthest away are the earliest? Are those the earliest we know of?
ooh. Well, after a certain point, it is not possible for galaxies to have emerged. That's because, well, I did mention earlier in the stream that these galaxies are more massive than we anticipated. But of course, if you go even further back, the temperature of the universe is way too hot for things to have come together to even form stars, let alone galaxies. The ones that we're seeing right now, which are these, they're called these little red dots, are what we believe to be are the earliest galaxies in the universe in accordance with our theories of galaxy formation and sort of the timescales of how galaxies have evolved.
Hey, I hope, Tarek, that helps you a little bit. Snow asks, how much hydrogen make up the universe and the galaxies? And I'm going to butt in and say a lot, but I'm sure you can answer that a little bit more and better.
Oh, I don't know the exact percentage. I might actually need to search that up. But most of the universe is hydrogen and helium.
Yeah.
What's really funny is that astrophysicists refer to everything outside of hydrogen and helium as quote unquote metals, which comes to show how important hydrogen and helium is. I might actually need to search what the percentage of hydrogen and helium are,
Yeah,
but
no,
it's
if
because, uh
no, I was going to say if you wanted to kind of look it up, I was just going to throw in and chat to say that we talked about this, that the whole story of the Big Bang development was the whole, what are they called? The Holtians and the Gamovians. Was it Holton? What's his name again? I forget the guy
Holtians?
he was opposing Gamoff's push of the Big Bang Theory in the 50s, I believe it was, or the 60s. I think it was 50s. It was around just after the development of the atomic bomb. I remember this whole interesting discussion. But anyways, the point being that there was so much hydrogen and helium in our sun that clearly the sun couldn't have made them. And that's kind of how it started pushing back further and further. Where did all this hydrogen and helium come from?
Yeah, actually, I completely forgot that this was a thing. I just had to Google it up again. But yeah, no. I mean, yeah, the reason why there's so much hydrogen and helium is primarily because of the Big Bang
Big
Theory,
Bang,
which
yeah.
led to the formation of these like really light elements, hydrogen and helium, in our universe.
That's right. Gamow explained it as that the majority of our universe was cooked in the first few seconds. What was it? Something. It took less time for the hydrogen and helium to form in our universe than it takes to cook a duck in the oven. I might
Yep.
be paraphrasing it poorly,
Yep.
but that was something that he said.
Yep. I mean, honestly, most of the crazy stuff in our universe happened within like the first few milliseconds, honestly.
Mm.
I think there are some timelines online where you can see like, when was the first elements made? And people think, oh, it was like hundreds of thousands of years. No, it was like genuinely after like the first few milliseconds.
poof, there's the universe. Exactly. It just it happened
Yep.
very, very quickly. Panic
Yeah.
asks, does our solar, I don't understand this question, so you might need to help me here. Does our own solar system and ORT cloud model the creation and ongoing behavior of larger collected gravitational bodies, such as spiral galaxies?
Wait, so sorry, could
Yeah, I
the
don't think
Oort
I
cloud,
understand it.
is it sort of, sorry, I'm just scrolling up to read the question, reread the
Yeah, I can
question.
copy and paste it again into the chat just so you can see it here.
Yeah, that would be great. Yeah.
Oh, model is the verb. Okay, so does our own solar system or an Oort cloud model the creation of an ongoing behavior of larger collective gravitational? Okay, that helps a little bit.
Well, in general, I'd say that a lot of the core physical concepts are the same. Um,
Mm.
the way that our solar system formed, like the disk, the protoplanetary disk, has to do with concepts of conservation of angular momentum, which led to these like flattened, rotating disks.
Mm.
Similarly, that's sort of how spiral galaxies are as well. Though there are a lot of differences, a lot of things related to, I mean, obviously, the solar system is and spiral galaxies are on very, very, very different scales.
Mm.
Um, there are different formation processes. Galaxies are driven by like dark matter merging with other galaxies and feedback, such as the explosion of stars and sort of how that material is recycled back into the galaxy. So there are a lot of differences, but I think at its core, like understanding rotation, revolution, orbits, there are some similarities.
Okay.
I hope that answers the question.
Yeah, I'm sorry. I didn't understand fully the question myself. Yaksha asks, are these universes before or after cosmic dark ages? So I'm not sure what that question refers to in terms of universe. Maybe it does mean, are these galaxies before or after our cosmic dark ages? Is that what the question meant?
I think it might also be referring to maybe like multiverse
I'm not
theory.
sure, Yaksha. If you could rephrase the question, apologies. Um,
Yeah,
um,
I think it might be doing with multiverse theory, but yeah, if you could rephrase it, that would be great.
Praised asks, isn't dark energy just a cosmological constant, though? What is there more to know than a number in an equation? Why is it considered so mysterious? Why is dark energy considered mysterious to you?
Well, I think there are a lot of discrepancies right now in dark energy.
Mm,
There's this one thing called the cosmological constant problem,
that's
which is
right.
that Mhm. We can measure the expansion of the universe, which is indicative of dark energy. But when we compare that to quantum field theory, I think we're getting like predicted values that are like 100 orders of magnitude larger than what we observe. So there are discrepancies
Small
across
percentage of error.
scales.
Small percentage of error.
Just a teeny tiny amount of error. Um, but yeah, another thing is understanding how dark energy evolves the universe. We are at a point where the expansion of the universe, like the rate of expansion of the universe is increasing. So um, it's accelerating.
Yeah.
And that's driven by dark energy. But there are a lot of questions that are left in terms of the theory, in terms of how dark energy connects to quantum gravity, all these different things. And more importantly, what even is dark energy? Um, so I hope that answers the question.
So even though we're saying that it's a constant in the equation, it's not. For some reason, it's not actually a constant. We don't seem to agree on what the constant even is. Is that a fair overview?
Yep, there are actually graphs out there that sort of plot the expected like expansion rate of the universe from, for instance, measuring the cosmic microwave background, or
Mm.
from measuring the explosion of supernovae, or from particle physics theories. And all of these things apparently are giving us different values for how dark energy should behave. So there's a lot of discrepancy going on. So
That
there's a
makes
lot
sense.
of open research. Mhm.
And there's a lot of scientists working on this, exactly. But you kind of opened the ground to let me ask my last question. And if there isn't any more, we are approaching a lovely and natural end to the Tofu Tech Talk. And I teach my lab rats about the end of the universe. There's three major ones that I talk a lot about: the Big Rip, the what is it called? The Big Bounce? No, not the Big Bounce. The Big Bounce is the conclusion. What is it called? The shrinking one. What is that called again?
The big
The
crunch.
the big crunch, and then the big bounce that follows. And obviously the big freeze, or the heat death of the universe. I'm a big fan of the heat death. That's the one I love because I love thermodynamics and it's just the most classical thing to teach about it. So my question is, if we were to observe the end of the universe, which end of the universe do you subscribe to?
Oh, okay. Wait. Have you heard of vacuum decay?
Oh, for feck's sakes, there's another one. All right, I'm gonna listen to this. All right.
This one is the scariest one. Um, so buckle your seatbelts. So the other theories that you suggest sort of happen at the end of the universe. Vacuum decay sort of will happen, or is theorized to happen very abruptly. Um, the idea of this false vacuum decay centers around the theory that our universe might not be in its most stable state. I don't know too much about the physics theories behind it, but the idea is that we're not in the lowest possible energy state. And
Oh.
a quantum tunneling event could magically cause this bubble of the true vacuum, the true lowest energy state to emerge. And this bubble would expand at light speed, which means that we would not be able to see it. Inside this bubble, the laws of physics would be completely different to the ones around us. And so it would destroy everything. So just imagine this like giant bubble expanding at the speed of light. There's no way to see it. And if it were to hit us, we would just evaporate. Like we would no longer exist. It would just be lights out all of a sudden.
So it's a bubble inside the universe that we exist in another universe of different laws of physics expanding into our own universe and taking over.
Yep, exactly.
Lovely. Well, that's another apocalypse to write down on the list. Thank you. Thank you for that, Z. We appreciate that. Here I was talking about the kind of the same idea of reaching a steady state, a thermodynamic steady state of equal energy distribution around the universe and dying from, the big freeze. But, there you go, chat. There you go.
Yep, we just disappear.
Well, on that note, Z, as we are ending, is there anything that you kind of like had in your head that you wanted to talk about and we didn't hit before we hit, or is there any last words you want to share here on Twitch?
I'd say after this stream, actually just prior to this, we were talking about streaming on YouTube versus Twitch, and
Mm.
I'm only streaming on YouTube right now, but after this, I might try considering Twitch streaming as well.
Could you do me a little favor and just write your username there or just type something in my chat so that people can give you a follow on Twitch if you accidentally possibly go live sometime on Twitch. But I had a link pinned regardless. So guys, make sure to follow in case we do get Z to stream on Twitch someday. But the other thing I wanted to do was I had your YouTube ready because what I wanted to do was share your YouTube link.
Hmm.
I have it here somewhere because I saw your posts earlier. Uh, Oh, your name comes up with X Files. That's interesting. What's that about? Sorry, give me 2 seconds, chat. I'm almost there. I'm not almost there. Why can't I get your profile up?
Actually, I did
Oh,
have
there we
one
go. Have it.
question
Yes?
that maybe might be a one last one to explore. I was actually curious, how did you get started with streaming?
Oh, years ago, 6 years ago. So I used to play competitively in a MOBA called Heroes of the Storm. And so I just kickstarted my stream by streaming my POV. I used to play a role called Tank, and I would do things like Shot Call, which was interesting for people to watch that point of view, someone who's making the calls, calling the initiations, things like that. So for years I used to do that, and then I realized it wasn't very good for my mental health, so quit that. But I built a small community on Twitch, and I stuck with it with the variety gaming and science communication.
Wow, that's such I feel like I've heard different answers, but that's such like an interesting pathway. That's a
It
good
evolved
one.
very differently. Yes, yes. So this whole persona of science communication variety streaming is less than 2 years old. But I used to just, go live, play with friends, um, play 5v5, say mean things to each other, and move on, kind of. All right. But thank you again so much, Z, for coming on Tofu Tech Talk. Like I said, you're a very special guest. First of all, astrophysicist, number one. Number two, our first physicist by title. And third, our first non-Twitch streamer. Maybe you will amend that in the future runs. So it was really, really nice to have you here and being a first in so many different ways. To my lab rats, make sure to follow on Twitch, but of course, make sure to follow on YouTube. Full videos. So Z does like the YouTube videos that I do, like proper videos, but you do live because I saw that psychology thing. Am I right in saying that you do live streams on YouTube too?
Yep, so I do have like several long form videos and I like to post shorts, but yeah, most of my content recently has been live streams and
Cool.
so yeah, thank you to okay, first off, thank you Tofu so much for, having me on. This was so great and I just love chatting with you and, thinking about like physics education and astrophysics and all these really cool amazing things in science. And thank you to the audience as well for the incredible support. I've had the chat open and this is absolutely amazing. Thank you.
I will say my private goodbyes behind the scenes chat because, I'm more important. But I will go into the AFK screen. I will raid you into Clem, who is doing an honor run of BG3. And, Clem has been doing IKEA-thon and stuff like that. So we'll give a little bit of support. But other than that, lab rats, I'll see you guys tomorrow, 12 p.m. Ireland time, because we'll be doing that physics thing on the front page. So that'll be really, really exciting. But other than that, bye-bye. Bye-bye, everyone.
Great, bye-bye.